the session. Over to you, sir.
A very good morning to all the participants, my dear students, and to the organizers. I'm really thankful to the organizer for inviting me in this one-week program, AICT sponsored faculty development program, and so I hope you are enjoying the series of lectures by the different experts in the field of MEMS and microfabrication. Today I'll talk upon the MEMS biosensors. Hope you have now understood the importance of the MEMS and the technology behind that, behind the development of the miniature sensors and actuators for the different applications. And you also can understand that it has the enormous potential in the deployment in various fields. I'll rather say its MEMS now covered almost all the field, starting from our household to the consumer applications, towards the military space applications, in the chemical industry, any industrial applications. Then you have quite a large number, a large volume of the sensors are being used by the automobile section, industry sectors, and of course in the biomedical sector for the healthcare area. These sensors are miniatures in nature, and it has certain advantages. That's why this area or this domain is I mean, expanding like anything. Along with the MEMS, now the nanomaterials, they are, you are aware of this, the nanomaterials and the potential, huge potential it has for various device, for various I'll share just some introduction to the course. So nanomaterials is nowadays is an important domain. So if you integrate that nanomaterial in the MEMS, can do a lot more things. Okay. In the field of, particularly in the field of biomedical and the healthcare section, okay, you can do a lot of things. A lot of research are going on in the microfluidic based and nanomaterial integrated lab on a chip development. Okay, now lab on a chip, this phase is quite old. People are telling it's coming up with an organ on a chip. Organ on a chip means can see can develop some organs in vitro in the microfluidic channels using the microfluidic platforms. Okay, and I'll now share my slides. Okay, I hope my my audio is visible to you. I mean, it is not visible. It is clear to you. I hope so.
Yes, sir. Audio is clear. Very much clear.
Okay. So now I'll share my screen. Can you see the
Yes,
PPT?
sir. Yes, sir. It
Okay.
is visible. Put in presentation mode.
Yes, sir.
Yes, sir. Now it is in full scale. Very
We
much
can see.
visible here. You can see.
Yeah. Uh, with this short introduction about the course topic, overall course topic, it is your MEMS and microelectromechanical system. It's a good topic and quite interesting topic also, rather I'll say. And different expert will talk about the various domains of the subdomains in the MEMS field. I'll talk about the MEMS biosensors. Okay, and um, I belongs to IIT Kharagpur and I'm in the department of in the School of Medical Science and Technology. That's why it's a natural choice for me to work in the sensor field, particularly on the biosensors fields. I basically works in the sensors, and one area is the biosensors for the healthcare applications and electrophysiological characterization of the cells and tissue using the MEMS platform, as well as I works on the inertial sensors using the MEMS platform. In the inertial division means it is for the defense and the ISRO, particularly in these two fields, lot of sensors are required, like starting from temperature sensor, pressure sensor to your accelerometer, force sensors, vibration sensors, rotation sensors, gyrometer. So I works on that field also. So these are the two major domains in my research area. Coming to the my the outline, my talk is the fusion of technologies and the biomems. I'll talk upon that, how this fusion takes place towards the biomedical application. I'll talk upon the what are the challenges, because already you are aware of the MEMS technology, particularly for the bio application, for the healthcare applications. What are the challenges? I'll talk upon that. And one very specific technology in a short, not technology, process I'll talk upon, which is very much needed for the bio application or healthcare application. Very specific this process technology. This is known as a soft lithography. I hope you are aware of the lithography part. So I'll talk upon that. So these will be some general discussion about the biomems area. And thereafter, I'll talk upon the R&D efforts that have been taking place in my lab by my various PhD and other students. And particularly, I'll talk upon the flexible flow and pressure sensors, imperimetric cellular growth dynamics, and the monitoring the biomechanics. As I have observed that few students from the mechanical engineering background are present, are attending this lecture, then I thought I'll share some of our research on related to the biomechanics. You'll see it is quite interesting. Okay, and then I'll conclude my lecture. So let me start with the Feynman vision in 1959 that he has mentioned, and most of us know these statements. There is plenty of rooms at the bottom. Entire encyclopedia could be written on the head of a pin. Fabricate a motor with a volume less than 1/64th of an inch on a side. Think about more than 70 years before, a great scientist has thought of this, what we are now implementing in the lab, in the commercialization as a product. Okay, this is the plenty of rooms at the bottom. So at the micro scale, at the nanoscale, many things can be done. In 1959 means it is 10 years back, 12 years back, the transistor was invented in 1947. And over the 10 years time, the silicon planar technology, VLSI technology, IC technology was on the way towards maturating the technology. And at that moment, when the device dimension was only, I'll say, few hundreds of micron, device dimension was hundreds of micron, not even tens of micron or the submicron level. It was on an average hundreds of micron was the device dimension. At that time, our great scientist Feynman has understood that lot of things can be done if you go down to the scale, atomic scale, at nanometer scale. And therefore he presumed that the encyclopedia could be written on a head of a pin with that submicron dimension or nanometer dimension, and we can fabricate a motor whose volume is less than this 1/64th of an inch. See, not only he presumed that many things can be done at the by scaling down the device dimension. This is all about the scaling down of the device dimension, but it is mostly in the electronics side. But he has also thought that some mechanical things can also be miniaturized. The dimension of a mechanical components can also be miniaturized to a great extent. He had that thought at 70 years back, and we are now working in that field. And globally, it is working. Many of the devices are now in the market. They are commercialized. We are using it. We are using in a very as a common people. In the mobile, we have the accelerometer, we have gyroscope, and many other sensors, which has a dimension and of the micron to submicron meter, and they are using the MEMS structure. So the MEMS was, I'll say, started in this year itself, 1960. But from the 70 onwards, it gets the really quite interesting, and the commercial products comes into the market. With this one side, now let us come what is the scenario in the healthcare sector in the India, where the population explosion in the developing countries puts the serious strain on the medical infrastructure, and that this we understand. This huge population is a burden for the government and have needs a giant leap in the medical infrastructure, and that cannot be done in a one day or 1 year. It takes years to have a total development, and we need the technological upliftment in the medical infrastructure. And there, these point of care devices, point of care rapid solution may give some relief and for having a good medical infrastructure. Okay. And these also, the point of care rapid solution may also give some solution towards the objective to meet healthcare for all. Healthcare for all, that means the medical facility will go to the poorest of the poor person, to the rarest sector of the society, remote village. Everybody should be included in the medical facility. And there we need a technological shift in the medical infrastructure, medical healthcare domain. Otherwise, it is not possible. Okay. The miniaturization technologies provides the benefit like lower production cost and the form factors and portability without compromising the sensitivity and accuracy. This is a must to get the healthcare for all. Only the miniaturization technology can provide the benefit like lower production cost. This is the one major issue. How we can reduce the cost of any medical treatment. It may be some clinical blood test, a sugar test, going towards a very high costly operation. Okay, and there we need some lower production cost, technology intervention in the through the robotic surgery. All these things are needed, as well as healthcare for all. Also, for all, to meet that objective, we should have the instrument which, or the technology which will provide a portability, and that portability of the system, of the instrument, of the devices. With that, we can go to the remote places to do some clinical test, do some operation, but without compromising the sensitivity and accuracy. So today, this should be our objective, and towards meeting this objective, we should have this miniaturization technology. Okay, and overall, as you have also you have already understood that this MEMS is an interdisciplinary approach. It needs the deeper understanding of the chemistry, biotechnology, particularly for the healthcare sector, for the biosensors. We need the deeper understanding with what is happening in the chemistry and the biotechnology at the molecular level. When coronavirus, it is interacting with the nanomaterial, we should understand at the molecular level what are the proteins that will interact with the nanomaterial, what are the electron transportation process that is taking place. Those things we should understand. Okay, so with this introduction, this is the MEMS. That means it is the integration of the mechanical and electrical component on a common substrate to produce a system of a miniature dimensions through the use of microfabrication technology. That you now understand that although it was started with a combination or the integration of a mechanical and the electrical component, but over the journey, 50 years journey, now this MEMS includes all different sectors. As I told, it not only limited to mechanical and electrical, it includes the chemical, it includes the optical, RF, the bio, all the fields are now integrated. And the MEMS device that actually operates, it should be in the different energy domain. Why I am talking about the energy domain? Because operation of these devices, you need some energy, and that energy will come from the electrical point of view. You give the electrical power, it will come. But the what measurement I want to detect, whether it is a temperature, whether it is a pressure, whether it is a velocity, force, anything, or chemical reaction process, pH sensors, whatever it is, the measurement that I want to measure, it should transform its energy into the electrical energy. If I want to measure the vibration of a system, the vibrational energy, that means the mechanical energy, will be transformed into the electrical domain through the MEMS devices. So there must be some transduction mechanism by which this energy conversion will take place. Coming from mechanical, it will go to the electrical, and you will get the vibration frequency and the vibration amplitude. Similarly, if I want to measure the pressure or temperature, the temperature, the energy, heat energy will be transformed into the electrical energy, and that will be measured automatically by the signal processing circuit. And today, most of the MEMS sensors, the input is has a large variation depending on what is the measurement, but the output is mostly in the electrical domain, because we want to get it in the electrical signal. The output should be in the electrical signal. Basically it gives us two advantages. One is the if I get it in an electrical form, then you can do the digitization, and after digitization you can store the data, and also you can transmit the data. Because for the digitization, these are the two major advantages we have. If I want to measure the temperature of a room for 24 hours time, then I'll keep the sensors along with the signal processing circuit and connect it to a computer. Then it will measure it, get the temperature for say every half an hour the temperature will be measured, and then it will be signal will be digitized, it will be stored, and we can also transmit the data to some nearby other computer. Okay. So output is in the electrical domain, whereas the input, it varies. Therefore, you have to, the MEMS device, the MEMS platform will transform this energy from one domain to the other domain. That is the whole scenario, and that is the basic principle. If we understand that, then you can make any kind of sensor for any application. That is the whole word. That's why I put emphasis on this. Operate in a different energy domain. That we must understand. The biological energy domain, we must understand that. And I'll talk upon the cell, the cancer cell viability, what it is. They are actually the energy that will transform, and we can characterize the cells accordingly through electrical means. I'll talk upon that. Due to the miniature size and the complex geometry of the 3D mechanical structure, fabrication of the MEMS devices is clearly beyond the means of traditional machine tools. This is the another aspect. Traditional machine tools means in the mechanical department, we know about the lathe machine, we know the cutting machine and all. These are the traditional or conventional machining process where we can get the device, a mechanical device, a cantilever, membrane, a gear, anything, any mechanical device, we can get it through the lathe machine by putting the material in the system, and it will cut or remove some materials, and you will get the structure. But one thing you have to know, that this is a sequential process. That means at one time you can only fabricate one gear or one cantilever. You cannot fabricate many gears or many devices, an array of devices you cannot fabricate at a time. And that means it involves the cost. Whereas for the silicon planar technology, I hope you know about all the planar technology, which involves the starting from the crystal, your crystal growth, diffusion, lithography, etching, thin film deposition. These are the very, very common and important process techniques used in the silicon planar integrated circuit technology. Okay, and there, if you understand the whole technology, whole the micro fabrication technology, you will understand it is you can fabricate an array of device in a single run. Hundreds of wafers can be processed, or thousands of similar chip can be realized in a single attempt. Therefore, it is a parallel processing, and that makes our whole device, the fabrication cost to be reduced at a much drastical way, and drastically it will be reduced. Because at a time you are fabricating 1,000 chips, therefore the total cost involved will be divided by 1,000 number. Whereas in the traditional machining tools, you have to, it is a sequential process, and therefore it consumes the not only time but also the machine, usage time of the machine and all. This all involves, and therefore the cost is huge. But planar technology gives you the much cheaper cost. Okay, as this is the advantage of this technology and taking this as an advantage, the batch processing technology is a batch processing technology. Therefore, the MEMS or the bio-MEMS sensors, whatever is fabricated using this technology, will have the cost minimum. Okay. And for the healthcare issue, this is one important aspect, so that the cost of the individual sensors should be minimum, because in most of the cases, the sensors are disposable in nature. Like a glucose sensors, where we uses these sensors and just using a drop of blood, you can get the glucose level of our body, of our blood. And once I measure that, I have to throw the chip, and the next time I have to use another chip. And many of the healthcare many of the sensors that is used in the healthcare sectors should have the disposable sensor kind of thing. And if it is a disposable, it should be cost effective. Okay, we cannot afford a huge money for buying or using a sensors only. Okay, so these are the different aspects we should know. One is how the energy transformation taking place, how we are getting that low cost by involving the miniature planar technology. And another aspect is that comparing the IC technology, this is a 3D structure. The MEMS is a three-dimensional technology. We are getting the three-dimensional structure out of a bulk material, which is not true for the IC. For integrated circuit, it is not a two-dimension. It is mostly we are considering the two-dimensional cases. Whereas for the MEMS, if you have a cantilever structure, if you have a microfluidic channel, that actually is a three-dimensional structure. Then, if it is a three-dimension, you have to consider how we can fabricate, how we will handle the three-dimensional structure, because many of these individual components will have a very small thickness, so it is quite fragile in nature. Uneven pressure will break down, or it will deform your structure. That is the one aspect, how to handle that. And another aspect is that today the simulation is quite coming up in a big way. Okay, instead of going to the laboratory and do the experiment, get the device and characterize it or measure it, first people will sit in the computer and I will do some simulation of my device. Whether I'll say check it, whether it will perform to the extent of my expectation, whether it will meet the specification or not. Therefore, I'll do the simulation. And today's simulation is quite vast and quite robust in nature. Okay, in every domain you have those softwares are available. Simulation can be done. And once I am satisfied with the simulation lesson, I'll go for the experiment in the laboratory to realize the sensors. Why it is so? Because many of the times we can see that the chemicals or the processing cost is quite large and it may fail. Therefore, before going into the lab for the experiment, I will do some simulation and check whether it is working or not. It is really feasible or not. I'll check it, and once I confirm, then I'll go to the lab for fabrication process. So while you are doing the simulation, you have to do for the 3D structure. That is an important thing. For IC, again, for the transistor or circuit level simulation, those who are in the electronics background, they know, or electrical background, they know all these simulation, device simulation you have, circuit simulation, process simulation you have. So you can do this simulation. But when I am talking about the MEMS simulation, that means if you have a cantilever, if you have a membrane, how I'll do the simulation? There also you have nowadays those softwares are available. It will be mostly in the mechanical domain. If I give a force in the cantilever, how much bending? So I'll do some simulation in the mechanical domain. But if it is a other sensors like RF sensors or a chemical sensor, you have a chemical module, you can do it. But all this simulation has to be done in a three-dimensional way. In a microfluidic channel, the fluid is flowing. So there also you can do the simulation, you solve the Navier-Stokes equation and all, and you will get the solution. But you have to do it in the 3D module, not the two-dimensional module. And there the complexity in the simulation increases, but it will give a very, very accurate results. So this is the another thing, another domain that we have to consider while doing the MEMS simulation. Now coming to the fusion in the BioMEMS. So fusion of technologies in the microscale. The photolithography, which is used for the silicon planar technology or microfabrication technology, and the medicine in the healthcare domain, they were total strangers to one another. But at present, they are indispensable partners in the biomedicine to envisage the scenario of personalized medicine. Because today this personalized medicine that is coming up, patient-specific prevention and intervention strategy. Patient-specific, not a very general strategy. Patient-specific. Suppose the cancers, for a cancer patients, how much dose I will give, radiation dose I will give, or chemotherapy I will give. It is a patient-specific. Can I? So this is altogether is a personalized medicine. Okay. What should be the dose of the radiation or the drug, concentration, how often, what is the frequency of that radiation? All this we have to calculate. And for that we have to know what is the tumor dynamics. You can do the simulation. That's why it is a patient-specific prevention and intervention strategy. This is the one point. Second point is the early detection protocol to identify the disease when it is easily subdued. Early detection protocol nowadays coming up in a large scale. People have to understand that. Okay, because any disease process, it will start at somewhere. Can I detect it at that stage only, at the early stage only? Then I can do. It can be subdued. It can be subdued. Okay. Otherwise, when it comes to the mature state, and there we do use the drug and all, which may not be the successful or fruitful in many of the cancer treatment. Therefore, the early detection protocols is coming up, and for that we need some tools. Not only tools, first we have to understand the science. What is the science behind that? So these are the 2 points. The third point, I mention it. Technology allowing for the long lives in the company of a disease as a good neighbor. So far we treat the disease is our enemy in the human living system. But can we have some technology which will allow the human beings to be with the company of a disease as a good neighbor? Let the disease be there, but without sacrificing the quality of the life. Without sacrificing the quality of the life. This is the whole things, and I like it because we can work in that aspect as a company of the disease as a good neighbor. Okay, and for working towards that, we should have a biomedical wireless sensors and the personalized healthcare and the beyond hospital application. Personalized healthcare or personalized medicine, patient-specific strategy, prevention strategy, you can understand. This is one important thing. Another aspect, beyond hospital application, Today, we don't have to go. We do not have much time to go to the hospital and stay for that 7 days for any operation. Can we do it in our house itself? Some of the things can be done, particularly for the diagnosis. You can do it in the home itself. Okay, so this concept, these words are coming beyond hospital application. BioMEMS is a device or a system constructed using the technology inspired from the micro nanoscale fabrication. These are analytical devices that combines the biologically sensitive elements with the chemical or physical transducer. Okay, so whatever the transducer you have, MEMS transducer is there, if you can treat, if you can integrate or combine biologically sensitive element, then it will be the BioMEMS. It is as simple as, okay. Biologically sensitive element, it can be a protein, it can be virus, the bacteria, cells, tissue, anything, organ. So then it is a biological BioMEMS. You have a many advantages. I have just mentioned few of them. Level-free technique. Most of the bio assays, it is a leveling process, fluorescent leveling process, and you can detect those reactions and all assay by detecting the fluorescent light under the microscope. This is the general practice, but if you use some BioMEMS, you can do the level-free detection of the bacteria, of the cells, or any other living elements. Can I do some level-free testing? Yes, for that I'll talk on that. So there you have to detect some non-biological parameters. You have to monitor some non-biological parameters. You have a biological parameters which will help you to detect using the fluorescent leveling. But if I do some optical characterization of the cell, mechanical characterization of the cell like Young modulus, or electrical characterization like the impedance, and that will vary those properties. The refractive index, Young modulus, impedance will vary if there is a disease progression takes place in the tissue. So if we can detect those non-biological parameters directly without using any fluorescent tab, then it will be level free, and that you can do using the BioMEMS. Small volume of the reagent sample. You can understand that for the blood glucose monitoring, it is only a drop of blood. By pricking the fingertip, you can do the glucose monitoring. CMOS compatibility, because the signals that you will get from the BioMEMS, in the electrical signals you will get it, and it should have a signal processing circuit, and that signal processing circuit it is a CMOS compatible. High integration, potentially low cost and low power consumption. Reduced time for the diagnosis. Whatever, in many of the cases, the diagnosis, the clinical diagnosis, it takes a few minutes time to put the sample there in the platform and get the output. So drastically the time has been reduced. Whereas in the clinical practice diagnosis, if I want to do the blood test, it takes about 12 hours time to get the result. But today it is possible that if you have those gadgets in the house itself, put the drop there, and you don't have to bother about anything else. It has inbuilt everything, and you will get the result within the 5 minutes time. And it is a safe usability because it is electrical testing we are doing, techniques we follow. Whereas in the most of the clinical testing we do using the acid and base, and miniaturization portability. Okay, wireless communication for the personal healthcare, beyond hospital application to the epidemic and the disaster zone also. Okay, so portability is a requirement. Miniaturization is a requirement. In the miniaturization, you can do the wireless communication for the personal health care. In today's society, as the lifespan of the human being is increasing, okay, and therefore in our society we have many aged peoples, octogenarian, or even more than 90, more than 100 years old people are there in the many houses. But they are bedridden, they are sick also. And just as an example, I am telling many of them staying alone, and suddenly if they fall down, can I detect it? If a aged person falls down, can I detect it? And the signal will immediately go to the nearby hospital doctors or to the security, so that they can come and they can help them. Today, using the accelerometer, a fall detector can be made, and which can be implemented in his stick, in his or her stick, so that that signal, whenever there is a fall, that means there is a change of G value. The gravitational force will immediately changes, and the signal will be generated, and that signal will go to the nearby station. Today it is possible. Okay, so these are the few examples I have given. Then why it is so important, the BioMEMS? Because there is a similarity in the sizes and the organization of the common structures. Let us see here what I have started here, say about 100 micron to the 1 angstrom level, where in the hundreds or the millimeter towards the micron, if you go, you have a RBC 20 to 30 microns, you have a plant cell elements, you have a bacteria within this micron range, and there the MEMS devices are, the dimension of the MEMS devices are within this scale, 100 microns to 1 millimeter or sub-micron. These devices can be useful to detect the biological cells or bacteria, because there is a structural similarity between the device and the measurement, what I want to measure. Structural similarity. If I go down, still you have a virus, you have a protein, and you have an atom. To detect this, the MEMS devices are quite large enough, 100 times or 1,000 times more larger than this, what I want to detect. Therefore, in the detection, using these devices, the detection will not be very accurate. There will be some noises. Instead, can I use some nanomaterial? Can I make the a nanoscale functional element which will be integrated in the MEMS structure? I'll not only use the nanoscale functional element or nanomaterial, but I will integrate them in the MEMS structure in the microfluidic device. I can integrate the nanoscale functional devices to detect the virus, protein, and other things. That means I need a functional, a dimensional similarity between these two. Then only the signal strength will go high. Okay. And as today we have those technology, the nanotechnology, MEMS technology, that's why the BioMEMS becomes much more important. In the microfluidics domain, you can capture a single cell. I can capture single cell. I can do the electrical impedance measurement. I can do of a single cell. I can trigger that cell with a drug, and I can visualize that its transformation, what is happening. Either in a mechanical domain, what is the change in the Young modulus of the cell membrane. All this I can do using the MEMS structure, because there is a structural similarity, or the configuration, those are in the same scale. This is the important. Okay. Coming to the some of the just two flyers I have for the to demonstrate what are the today's BioMEMS, why they are so important. So MEMS versus BioMEMS. MEMS use the micro-sized components such as sensors, transducers, actuators, electronic device to sense. Many of the sense used in a consumer product and the other areas are also found in the biomedical devices. Like I told you, for the aerospace or for the any automobiles, you require the accelerometer. I works in the accelerometer field, and so that accelerometer can be that is accelerometer means it is a force sensors. I can use it as a fault detector for the for aged people, fault detector. I can use the gas sensors for many biomedical applications. I can use the pressure sensors which will used for the aerospace to see the what is the height or the of the satellite. That pressure sensor can be useful for the blood pressure monitoring also. So there are a lot of scope are there to use the different sensors. MEMS pressure sensor found to be in the blood pressure monitoring, infusion pump, catheters, and intracranial probes. Okay. Biosensors are analytical device that combines the biologically sensitive elements with the physical or chemical transducers to select or quantitatively detect the presence of specific compound. So you have a pacemaker. From the pacemaker, the signal will go and it will trigger the expansion or the contraction of the heart muscle. And there, finally, if this signal will come and it is the wires is attached to the muscle through some electrodes. That electrode, through this electrode only, the signal will be delivered to the muscle, and muscle will contract like anything. Okay, so you need that one thing. Every components should be biocompatible. Okay, and the sensor should work in the biological environment. Sensors should work in the biological environment, and these are the challenges. These are the challenges that we must solve it for making any BioMEMS a successful BioMEMS devices. If anything comes in the MEMS without, I mean, have the applications other than the biological application, we don't have to worry. You just fundamentally clear about the functionality of the device, and then you can realize it and go for the application. But if it is a biomedical application, healthcare application, those issues are there, and then you have to prove that they are biocompatible. If it goes inside the body, then implantable device, then you have to go for the very rigorous biocompatibility test. Okay, in both way. Not that the device which is implemented in the body, it will be I mean, adjustable to the bioenvironment. Not only that, the foreign things that I have incorporated in the body, that should not have any detrimental effect or the negative effect in the body tissue. Both way we have to see. Both way we have to see that. Okay. That's why it's a challenge. Biocompatibility is a challenge. Here I have just shown some of the MEMS or BioMEMS devices. I just talk on this a few things, this very common things that I have taken from the net. Here you see that a insulin pump. Insulin is used to regulate the blood glucose. Okay, if the glucose level goes high, then you have to deliver the insulin. And now it is a diabetic, and diabetic is a prevalent disease in India or globally. So very often people have to test the blood glucose, and if required, the insulin has to deliver. And there it involves a costing. It involves the blood sample. This much amount of high volume of blood sample has to be taken, go to the clinics, did the test, then required insulin has to be delivered. It not only involves the cost, it also involves the time. Now these devices are commercially available, not in India but in abroad. Here you have a glucose sensors which will detect the glucose level of the blood by electrochemical process. Okay, and monitor that. So online monitoring is possible of the glucose level. And once you see it detect that glucose level is high, then inside this gadget you have a pump which will be activated, miniature pump, micro pump, which will be activated and deliver the insulin into the inside the dermis layer. So insulin can be delivered with by some electronic control, and that feedback will come from the glucose level of the blood. This is the total gadget. Okay, and for that I don't have to go to the clinics. I just wear these whole things, and it will be in the pocket, pockets of devices, and so lightweight also, and it does not require any constant monitoring. You just put it together, automatically everything will be done and insulin will be delivered. This is the concept today. Other things, it is the cantilever structure where the antibodies can be the antibodies are coated, and virus, the specific virus can be detected using this cantilever sensors by a deflection. As the virus will attach and there will be some reaction, this reaction process will take place. So depending on the number of viruses attached to the cantilever, the stress inside the stress on the surface of the cantilever will increase, and that way it will bend and the light deflection of the light changes. And if I can detect this, you can get how many viruses are present. The other one, I'll talk on this area, the cell culture and the bioimpedance. I'll talk upon that because it is one of my research field. Another one is the standard neuroprobes that has been fabricated using the MEMS technology. You can see this fine tube, tip, very fine tip, only few nanometer dimension, because the neural signal, to the neuron, axon and neuron, the electrical signal will transmit, and people want to detect those signals for the neuro disease detection. Okay, you have to analyze the signals. How will detect that electrical signal? Because it is, first of all, it is the amplitude is very small, and secondly, I have to access the probe. I have to access the neuron through some probe which will detect or carry the signal to my outside instrument. So for that I need a needle like this. The needle tip should be only few angstrom diameter, so that it will be placed properly in the neural area, and you can the electrical signal will propagate through this needle to my external instrument. People started this this research using by etching the silicon material, and they are successful in that. These are some of the silicon based your microneedle, but when they put it and use it as a probe for the neural signal, the neural signal detection, very often it was observed that the neuron is getting damaged. Neuron gets damaged. Why? Because the neuron is a biological entity and silicon is your solid material, and there is a three order magnitude difference between the biological, this neuron, and the silicon. Therefore, any probe that touches with that young modulus, easily the neuron will easily get damaged because of the mismatch of the young modulus. Then the scientists work on how to get a polymer based needle, because polymer is a soft materials and the young modulus of that very much matches with the neuron. So they come out with the technology to get that polymer microneedle, and the signal can be captured and easily, and you can get the you can do the measurement of this. So this some of the glimpse of the BioMEMS I have shown here. Now going to the challenges. Challenges I told about the biocompatibility, life of the device, retrieving data out of the device requires the fast and solver for the multi-domain solution, and takes years from concept to product. Particularly for the BioMEMS, it is a must because it has to go through the different animal test, human trial, all this has to go. And for any sensors or actuators, there will be a drifting. There will be drifting. Today, whatever the calibration curve you have, but after 1 month, after 1 year, that characteristics will shift to some extent. This is known as a drifting. Why there is a drifting? Because this is the overall environmental effect on that. But if it happens in my pacemaker, if it happens in my other implantable device, after 1 year, after 2 years, my signals, pacemaker signal is going up or going down, then my body will be affected. So, and that drifting, that means this drifting has to be restricted. And this is one fundamental issue that people are working on that, particularly for the biomedical or implantable devices. Okay. The other issue that requires the fast solver for the multi-domain. As I told, you have a lot of simulators are available, softwares are available for the simulation purpose. And this MEMS works in the multi-domain aspect, electrical to mechanical, mechanical to chemical, or the heat energy to the electrical energy transformation. In the simulation, it is a multi-domain simulation. The heat energy in the heat domain, thermal domain, it will do the simulation, get the output, and put that output as an input in the electrical domain or in a chemical domain, and then you solve that one. So that's why it is a multi-domain simulation. You have a microsystem component. In the implantable wireless microsystem, you have many things. Onboard power supply you require. It should communicate the bidirectionally through the RF interface. Have onboard signal processing capability, and constructed using biocompatibility materials. Transducer suffers poor signal to noise ratio, thus requires onboard interface electronics. Any implantable device that is inside the body has to transmit the data outside. When the signal will come out, will be transmitted to the outside, because of the presence of the tissue, a thick layer of the tissue, the signal will be attenuated. It will be absorbed by the tissue. And therefore, onboard interface electronics is preferable. That means that whatever signal is getting detected by the sensors, the inside that body itself, the signal processing will be done, and the final signal will be transmitted to the outside. So we need a interface electronics board. Okay, and to have the interface electronics, I must have a very good power supply. Very good power supply. Okay, and that power supply, very good means it should have a good amount of wattage should have, or energy should be preserved. But at the same time, as the whole package or the whole system will have the sensors as well as the interfacing circuits, so it will consume some amount of power. That means you have to work on the signal processing circuits and the sensor part so that it will require minimum amount of energy, minimum amount of the power consumption. Therefore, you will get a balance, or you can have a maximum usage of your power supply. Packaging is an issue. Packaging and encapsulation is a challenging task. It must accomplish to the product electronic from the harsh environment while providing access to the window, protect body from hazardous material. As I told you, both way it should be. Product electronics from the harsh environment and protect the body from the hazardous materials inside the microsystem. Both way it has to be biocompatible. Okay, and this is a challenging task. And another issue, as I told, for the MEMS, the MEMS or the BioMEMS devices, say the measurement that we want to measure, that has to interact with the sensor part. Suppose I am measuring a pH I am measuring what is the pH of my say inside my body at the different parts, what is the pH value. I should put that pH sensors inside the body, and then the pH sensor should work with the chemicals that is present there, and they will interact and you will get the signal. While for this, the sensor has to interact with the environment. Not only pH sensor, suppose it is a pressure sensor. So the pressure, to measure the pressure, the sensor has to interact with the microenvironment. If it is a temperature sensor, again the temperature has to be sensed. That means there you need a interaction between the sensors and the environment, which is not required for the IC. I mean integrated circuit chip. There you give the input signal, you will get the output. But here, to detect the signal, the sensor has to interact with the microenvironment. And that is a challenging task. In many of the cases, the biocompatibility fails in that way. Okay. Choice of power supply, I have already talked upon, and bidirectional wireless communication is essential for the implantable microsystem. As most of the silicon planar technology is used to realize the MEMS structure, but to have a disposable low-cost devices, we should not rely on the lithography. We should have a technique which will be much more cost-effective, and that way it will be disposable in nature. And therefore, we need a newer kind of material also. Silicon glass is no longer can be useful because of those limitations. Silicon, not much biocompatibility, and as well as it is a costly thing. So with the different limitations and the issues, these things we can avoid. And instead, as well as these are the very rigid material, I should get some flexible material also. Flexible, biocompatible, and a low cost. Considering those 3 points, polymer is the answer. Okay, is the solution. So polymer can exist in the various form and can get a arbitrary shape is possible. It is biocompatible, and you can do easy machining by non-lithographic method. I'll just talk upon this, what is non-lithographic method. Few of the polymers are SU8, PDMS, polydimethyl siloxane, PMMA. So various, polymers are now coming up to have the BioMEMS devices on that. Here, what is a soft lithography? In the soft lithography, an elastomeric stamp with the patterned relief structure on its surface is used to generate the patterns and structures with feature size ranging from 30 nanometer to 100 millimeter. See the range. So it is a kind of a stamping. In the post office, we have seen the stamp. There is a mustard piece, and it absorbs some ink. And then if you press it on the papers, you will get the replica of that. The whole idea can be useful here also. In the post office, this stamp is a two-dimensional, rather I say. It is a two-dimensional, but here we have to use a three-dimensional. Not only X and Y, but it also has a Z direction. If I want to make a microfluidic channel, so it has its length, width, and height. How can I generate the height? Here, some of the soft litho devices using the soft lithography, it has been shown. Here you have a microfluidic channel where you have a X and Y and Z also, and it is a dimension is less than micron order, and you can get a very good and complicated configuration, complicated structure you can generate very easily. Okay, so you have several advantages, and most of the time we have observed that PDMS, as I told you, polydimethyl siloxane, it is a biocompatible, and of course, as it is a polymer, or elastomer, it is a flexible in nature. This flexibility, these characteristics also play an important role for the BioMEMS. Okay, and how I'll create soft lithography polymer? So it is a two-component. This PDMS is a two-component. Your chemicals. One is a polymer, another is hardener. Mix up at a particular ratio. Mix it very rigorously. Then you can do some treatment to remove the air bubbles, and then you can pour it on some patterned substrate. This patterned substrate is nothing but we call it is a mold. It is a master mold. That master mold, actually, here you can see this is a master mold. It is having some microfluidic pattern. Okay, but this microfluidic means in this area that there should be some ridges so that fluid can flow. It can flow. But in the master mold, this area should be ridge like. That means it should have some height on this surface, master mold surface. Whatever I want in the actual device, the master mold should be negative of that, just opposite or replica of that thing. Then only you will get a microfluidic channel. So once you make this this mold, it is done by silicon technology, silicon fabrication technology, by etching and lithography process. And once you get that, and it is on the in a solid and rigid substrate like silicon and glass, you can use it. Once you get that, then on that you pour these treated chemicals, treated polymers, and it is a viscoelastic material. After putting that, you can do the spin coating so that you will have a uniform layer. Uniform layer will be coated on that, and once it is coated, then you do some heat treatment in the oven so that polymerization will take place. Polymerization means at a high temperature you will get a carbon chain, longer carbon chain, and it will, instead of viscoelastic material, it will come to the solid material. And after heat treatment, you can peel off the whole material like this. Once you peel it off, the structure which is present in the master mold will also be transferred onto your soft material, but it will be in the opposite way. If you have a ridge-like structure over here, you will get a groove-like structure in the device. Okay, and this is a soft lithography. And once you do that, then this master mold can again be used for the next device. As we do the stamping, many times I can use the master mold. Here also, the master mold can be used many times. Therefore, it is a cost effective. First of all, it is a cost effective. And second is that you are using a polymer, which is again is a cost effective things, and the whole process, it is a very rapid process, and you can get a replica, many replicas in a short time. And altogether, material cost, the processing cost, and other cost involves are quite low. That's why it is a cost effective. And as being a polymer, it is flexible in nature. So with this now introduction, as it covers much time, so I'll just talk upon quickly about some medical diagnostics in the MEMS perspective. Some R&D initiative we have taken it in our lab. One is the thin film buckling assisted polymer based flexible flow and pressure sensors. Here you can have just introduction part. Now the flexible technologies are coming up. Flexible solar cell to the healthcare sectors, automotive industry, electronic display system, and definitely in the defense and military applications, these flexible technology are coming up. Okay. Here, what basically is that all the devices, maybe a silicon diode, maybe a transistor, maybe a microfluidic device, maybe a biosensors, can we fabricate on a polymer, which is a flexible nature. That is the flexible technology. And maybe some of you are aware, now the technology is away from this or moving forward from this flexible technology. People are using the paper, the common paper which we use as a writing for the writing purpose is used to fabricate different sensors. So some step forward towards the flexible technology. Okay, and that's why it is very much useful for the BioMEMS application. Particularly, it is for having a very low cost, easily available. All those factors are advantages are there. Okay. Now, today I'll talk only on the flexible sensors, which is actually the substrate is your polymer. Substrate is your polymer. As being the polymer substrate, so what is the Young modulus? Young modulus, I told, it is low enough, or it is comparable to our tissue Young modulus, tissue or cell in Young modulus. And on this polymer, many different materials, including the metals, has to be deposited and patterned, and you to get the devices. Now think about the polymer where I have shown here, it is bending. It is flexible, so you can bend it. As your polymer being a low Young modulus, you can bend it, just like a rubber. What about metal? These are suppose aluminium or say gold metal have been deposited. While can you bend it like this? No. But here, the thin film of those metal is deposited on this polymer, and then it was patterned, and then it was just bended like this. While this whole sheet was bended, as being the polymer, there will not be much damage here. But what about the metal film? Having a very high Young modulus, although it get the bending shape, but once you release, you see there will be some crack formation on the film itself. And if you do this bending process repeatedly, your film get damaged. Your metal film get damaged. And if I make some devices on the polymer substrate and finally you have some interconnection, metal interconnection, then while it goes to the rapid flexibility, bending of the devices, very quickly, the devices will get disconnected and you will lose the electrical connectivity of the device. Then, what is the solution of that? This is the fundamental problem of using the polymer substrate. One of the fundamental problems. Basically, what is happening? If you take a polymer PDMS like this, I have shown the cross-sectional view, you heat it and you deposit some metal film over there, thin metal film over there. Now this metal film has a very high Young modulus compared to the PDMS. And once after deposition, if you cool it down, so the PDMS will get the initial shape. As it gets the initial shape, so at this surface which is free, will get some buckle shape. And the film should be, I mean the metal film should get the similar buckle shape while the PDMS surface is relaxed. Here it was in the tensile stress while the deposition takes place. After cooling down, it should be relaxed. The tensile stress is released and film will get buckle shape like this. This is the your microscopic view. So you can see the film is not very uniform. There is a buckle exists in the film, and these buckles are random in nature. Because there is a compressive stress in both the sides, this not only this side but also from this side, so it will form a random buckles over there over entire surface. Entire surface it will happen. Now you can do the frequent bending, but after frequent bending, as the buckles are random in nature, it will get some cracks over the surface. So your device will not be functional after a few times. What we did, we do some engineering, surface engineering over the surface, so that instead of a random buckling, because of the equibiaxial compressive stress, you do some pattern on the surface, deposit the film so that the buckle formation will be parallel only in one direction. It will not be random. You are doing some surface engineering so that your buckle formation will be parallel only in the one direction, not in two directions. And if this is the buckle formation in this direction, if you stretch it along this direction, then it will be it is advantageous for you, because the metal film which is having higher Young modulus will be stretched in this direction, and there will be a change of resistances will happen. So, and you can do these changes many times, do the bending many times, because the buckles are perpendicular. Buckle formation is perpendicular to the stress direction. And I can utilize this property to make some devices. Okay. So here we do some surface engineering so that you will get a controllable buckle formation in particularly in one direction. It has some use. The use is that here I have shown you some of the ACM pictures, how this silicon film, thin film or metal thin film can get buckles over only in the one direction. Okay, and these are the two different mechanisms you have. We have used this mechanism instead of this one, so that if first you take the PDMS film, you do the pre-stretching. Initially you do the stretching, and then you deposit some metal. Once you, after deposition, you release this stretching, you release the stress, and the surface will get buckle shape. Along with that, the film will get buckle shape in the one direction only, not in the two direction, because the stretching was done in one direction only. Okay, so you can do it, but right now, not only in one direction, you can do the stretching in both the direction in a very controlled manner. Then the buckle formation will also get some very complicated shape, and that you can utilize it for operation of your devices. Here we have done it particularly for one application, that is a to make a flexible flow sensor for catheter integration. Catheter which goes inside the body for different operation, and as it goes against the blood flow. So can I detect the blood flow in a real time? For that, I have to integrate a flow sensors at the tip of the catheter. For that, as the catheter's surface is a circular in shape, so I cannot use a very rigid substrate. I have to use some flexible substrate, put a resistor over there, which will be conformally integrated, over the entire catheter surface. Therefore, instead of silicon, we use the PDMS as a substrate. On top of that, we have patterned the surface engineer and get some nichrome metal film deposition and patterning by the lithography process. It will get a shape like this, and while doing this deposition and patterning, you get unidirectional buckling. And once you get the unidirectional buckling, the stretching in this direction, because as it goes from flattening surface to the curved surface, there is a stretching along this direction, and the unidirectional buckling will help in bending of the film along this direction. Here I can show you just pictures. I have shown how the individual resistors on PDMS we have developed, and once you develop it by using a batch fabrication process, then you have to release. It will automatically release in some chemicals. Okay, PVA chemicals, you have to use it, and because PVA is a water soluble, so individual resistances will just come released and float. And you can take the individual resistances and go for the device packaging. So it is the microscopic view of the simple resistor, and this resistor was used as a flow sensor. And here, how much bendability I have achieved. You can see this is a ACM pictures, where you can see that this device is integrated at around a catheter surface, which has a radius of curvature about 2 millimeter. 2 millimeter is your radius of curvature. Around that, our sensors was integrated, and we took the electrical connections from there. And using this, we have made the flow sensors, and we are successful to some extent. While develop this technology, next we have attempted to get a flexible pressure sensors for the biomedical application. I'll skip these things, and here also for the endoscopic catheter inside the body, it is quite useful for getting this kind of a pressure sensors to monitor the tissue damage while the endoscopic process is going on inside the body. And tissue damage in the sense that for robotic surgery, sometimes some uneven pressure may damage the nearby tissues, or then you have to use the pressure sensors. If there is a laser treatment, then because of the uncontrolled power of the pressure, power of the laser, nearby tissue get damaged, may burn out, and therefore you need a temperature control. So not only pressure, temperature sensors, integrated catheter is also a demand for endoscopic surgery. Flow sensors, pressure sensor, temperature sensors, all are in demand to have an integration with the endoscope or with the catheter for the robotic surgery purpose. So we have worked to some extent towards this direction, and we have developed the pressure sensors, and you have a different application. What are the different pressure? It can work from 1 Pascal to 100 kilopascal for the different applications. And based on the applications for the robotic hand and all, you can develop the pressure sensors of the different dynamic range also. Quickly, I'll go through that. So here, we have used the PDMS as a flexible membrane. Over that, we put the gold as a thin film and gold as a strain sensing element. So we deposit the gold and then we have patterned the gold's thin film to make the resistance. Now, this is the sensing part. Basically, it is a AU strain sensors or a resistances. How the resistance is configured? It is just like a Wheatstone bridge. 4 resistances are there. 2 resistances are in the periphery. One is this resistance R1. This is the R3 at the periphery, and the configuration is along the axial direction. Whereas in the inside the circle, inside the membrane, you have a, this is another resistance R2 and this is another resistance R2, 4. And to get this access of this, the 4 arm of the Wheatstone bridge, you have the 4 bond pairs extended towards the periphery. So altogether, this will make a Wheatstone bridge circuit. Now the configuration or the layout is such that here at the periphery they are aligned towards the along the axial direction, whereas inside they are not in axial direction, they are in the in a circumference direction. Okay, that means the periphery, the stress will be much high in this direction. Therefore, they are extended, their arms are, resistor arms are extended in this direction so that maximum change in resistance you can get it. In the inside, as the pressure will build up, the PDMS membrane, it will deform, and maximum flexibility or maximum extension you will get around the circumference. Therefore, the resistances are aligned in this way only. And once you do that, then you can make a Wheatstone bridge circuit and get the output voltage. So with this design, we have implemented these things in this way. And this is the whole process technique. I'll not talk much of this, but here, so this is the resistance in a single set, the buckle manipulation. So we deposit the gold film on the PDMS. So there will be a random buckle because of the uniform stress along the X and Y direction. But if you make a patterning, make a resistance like this, and then you can go for heat treatment. In the flow sensors, we did not do the heat treatment, but we managed the surface engineering. But in this case, we did not go for the surface engineering. Rather, after making the pattern, we do some heat treatment. Already, after patterning means already your material is having some restricted dimensions, in the sense that in the X direction length is high, Y direction that width is very small. So you have a dimensional restrictions. Then you do the heat treatment. In the heat treatment means you just put it at a oven, little bit high temperature, so that both will expand. But because of the material, I mean mismatch of the Young modulus as well as the dimensional restriction, you will get a uniform buckle only in that one direction. Uniform buckle only in the one direction. Okay. Here it is at 25, sorry, here from 25 we heat it to 160, and here again if you do the bring down the room temperature, you will get the buckle in this direction only. So by this is another technique by which you can control the direction of the buckles in your own way. Okay. And here it is a microscopic view how it will look like, and the resistance that will change, it will have the strain versus resistance, which is non-linear. But in the initial phase it is a linear, but as you extend the straining, that means you increase the strain, the flexibility in one direction, the amount of the change of resistance will be in the non-uniform, and that also varies for the different dimensions. So it's a complex phenomena, and we have utilized only the linear portion to make the our devices. This is the whole process to get a device, and here I can show you we have made the 12 array of the pressure sensors on that. Finally, you have to make a bonding, packaging, all these things are there. And finally, we have measured the the response of the pressure sensors for the individual pressure sensors through the Whiston bridge output. We have measured it for the different time, for the different pressure, and then we made a array of pressure scheme, just like to mimic a sensors like a aquatic animals, a fish. It has it can sense. So it has in the screen itself, it has the pressure sensors. Can I make such kind of a sensor scheme? Yes, you can make an array of this. We have made a 10 array having the same Whiston bridge structure. That is quite now technology is established, but getting the packaged and get the connection out of that is a major challenge. That you can understand from this. Okay, making some of the connections out of this is really very challenging issues. Okay, and with that extent, we just made some assessment of that, a measurement of that sensors, and underwater we did it, and in that way we have developed the pressure sensing study. So I'm not sure if I have much time. Yes, because sorry, do I have any time, or you will?
Sir, I mean, we have the time up to 11, so we have done with. So
Yeah.
we can take some questions if you permit. And then,
Yeah, sure. So I'll
because
stop
the next
over
schedule,
here.
next
Yeah.
schedule is at 11:30. So
11:30. Yeah, I understand that.
And before
Therefore,
that, we have to give a break for the participants.
Some-
To
Sure.
So we can take the question answer session. We can have the discussion. We have
Yeah.
covered many more things, so we can take some discussions here. No.
Sure. I'll because I could not manage the time. Therefore, this is the bioimpedance, and I told about the biomechanical things. I'll skip that. It is also interesting for your getting the some cellular mechanics in that. So I'll conclude here. Lot of things is possible, is a promising using the MEMS to get some bio devices for the diagnosis purpose or for therapeutics purpose also, and the very easy patterning of the PDMS polymers to avoid the costly fabrication process, and can solve the many complicated biochemical and physical processes with the fundamental understanding. With this, I will conclude it. And for this, I must acknowledge my PhD students like Devasis Manji, who worked on the flow sensors, Obhijit Kakati, who worked on the pressure sensors, and Devanjan has worked on the bioimpedance, and the Jyoti works on the biomechanics part, and some of the sponsors and my colleagues also. With this, I'll just conclude here, and I am ready to take up some questions. Yes, participants.
Yes, participants, please have a discussion. If you have any doubts you are having, you can discuss with Professor Soumen.
Yeah, any question?
If any questions, participants?
I think there is no question. And
okay, there is one question in the chat box. Professor Miriala Vidir Badargaon is asking life of biosensors. How much is the life of biosensors?
Yeah, it's a good question, and really the life of the biosensors One way I can say most of the biosensors are disposable in nature. Okay, and so for the dialysis purpose, whatever biosensors are used, it's in vitro outside the body. So once you use it, then you have to throw it out. That's why it should be disposable in nature. But the sensors which goes inside the body and like implantable devices, there is some time limit, not very high, but people are trying to make it make the lifespan quite longer, so that the frequent operation can be avoided. Okay, this way I can say only.
Connection with the same. One more question is there,
Yeah,
sir. How do
degradability.
you
Yeah.
analyze the degradability of this biosensor in future?
Yeah, degradability, it is the you can do once you fabricate any biosensors, then externally we can do some testing to get the biodegradability. Like we say, for making the or to test the biocompatibility, you have to do some test. That means you put the sensors after development, you put the sensors in the some biomimicking environment and see how it will perform. Similarly, the biodegradability also, we can do the testing, in vitro testing, by creating some bio environment in the lab, put the device in that environment and see how this degrades. Just as an example I am giving you, suppose I have made these pressure sensors. So once after making that, I know that PDMS is a good biocompatible. But for what about the gold? Because the sensing element is my gold. Gold is also biocompatible. Both way it is biocompatible. But the gold is now in a thin film, and that is also patterned on the PDMS. How it will work? Is there any degradability? Yes. So for that, once I made this device, then I put it some of the bio environment. On a petri dish, I put it there and I kept it for over days. Then after say 7-10 days, you can observe that whether my connectivity, electrical connectivity is getting degraded or not. And I have seen that in the initial phase, yes, there was a degradability of my electrical connection. Because the degradability of the electrical connection means the thin film is getting peeled off from the polymer substrate because of the adhesion problem. So then I have worked on that, and our student worked on that, putting some surface treatment of the polymer. Then the adhesion property increases, and we have overcome this issue. So this way, in the ex vivo condition, you can test some degradability issue before going to test for the animal test. Okay.
Sir, may I ask one question to you, sir?
Yes.
Go ahead.
Sir, what is the reliability of pacemaker?
Nowadays, pacemaker is quite reliable. Nowadays, pacemakers are quite reliable. Earlier, in the past, see, the pacemaker, it is in the body. In the past, it operates with a battery. And in past, say 15 years back, 20 years back, after 5 years or so, you have to change the battery. Okay. And you have to, the patient has to go through the operation again to change the battery.
Sir, how to make the charge, sir, after discharging this battery in the pacemaker?
Yes, now you can do. Now you can go for the rechargeable pacemaker, so that after certain years you can recharge it from outside by power wireless power transmission. Wireless power transmission, it is possible. It is possible to some extent, but there is a challenge. For transmission of the data, wireless transmission of the data, you need some inductor. Now, for the data transmission where the signal strength is very low, there the induction, the area of the inductor is quite low. But if I want to transmit the power, in that case, the area of the inductor, it has to be very quite large, which is a challenging issue for the pacemaker. Okay, because
what is the life
so
of this battery of this pacemaker, sir?
now battery of the it is quite it has a very good a good life. Longevity is very high. Because people have did the research, and now 10, 15 years, 20 years easily it can go.
Wow, very good, very good.
Basically, what people are doing, they are making the circuit in such a way that the total power consumption is getting reduced and reduced.
Okay.
Nowadays, you can see once the circuit is not used, then it goes into the sleeping mode. Sleeping mode means the power consumption is very low.
Okay.
So those kind of designs people are doing. Okay.
Okay.
Sir, we can we use sir?
Yeah. Tell me.
Sir, could we use this biomems in diagnosis of the gastro problems like capsule endoscopy in terms?
Yeah. Capsule endoscopy, actually, I like that one, but I did not put that slides here. It's a capsule endoscopy means instead of using a catheter-based endoscopy, a patient can take the pill in the morning, and in the pill itself you have a sensors, you have a camera, you have a light, you have a batteries all together, and that the size of the pill is of the capsule. Just inhale and it will go through the intestine, and while it is in those environments, they will take the picture in the IR, through IR camera, it will take the picture images. Along with that, I told the pH sensors. In the different parts of your intestine, you have a different pH. It can sense what are the different pH at the different locations. Similarly, the temperature or the oxygen content in that zone, those sensors are available or integrated with the pill. And once they measure all this, the data has to be transmitted outside because it is in a real time. The patients who take the pill just put a cassette in his pocket, and over the 24 hours, as the pill goes from or travel over the length of the intestine, so it collects the data and it will transmit it to and record it into the recorder. And then in the next morning, the doctor can see the cassette for diagnosis purpose. This is the whole concept. Okay. And first, some Israel group, they have developed over probably 15 years back. But right now, I have not seen so much progress. In India, there is no commercial product available right now. I do not know about the abroad, but it was first invented by some Israeli group. Okay. And it is quite interesting. It has some prospects also. And patient don't have to be in the hospital. Just take the pill and go for work for his job. Whole day he will do. Next morning, the doctor will only see the cassette, where you will get all the sensor data, the images of all the different parts of your body, the intestine, through which the capsule moves. This is the whole concept today.
I think that is more reliable than our traditional trend of
yeah, that is true. Not reliable, I'll say, rather it is a more comfortable. Yes. Patient your gets much relaxed, relieved, and instead of a endoscopic operation. But I am not sure because I'm not updated in that area. Although, as I told, although it was invented 15 years back, probably 15 years back by some Israeli group, but I have not seen much of the product, commercial product, still now in the market. Maybe there is some issues, or maybe I am not updated. Okay, but it's a very good product.
Thank you, sir.
Thank you all. And
Yeah,
I
good morning,
again
sir.
once
Thank
again,
you, sir. Thank you
yes.
for, yeah, one more question, I think, sir. Yeah, please go ahead.
Yeah. Good morning, sir. Soumen Das, sir. Very nice talk, sir. Thank you for your valuable information for the upcoming researchers. Actually, I got two answers for my questions. That is, for soft to develop my biosensors on polymer is always reliable than when compared with silicon and glass. That is really good thing I got. And I would like to know something about soft lithography, sir. Actually, I know about only lithography. Uh, so this facility is in which university it is available in India, and how it has to develop if you want to develop.
For going to the soft lithography, you do not require much of the infrastructure. Do not require much of the infrastructure. That is the advantage compared to the your common standard lithography. Standard lithography, you need a your lab development cost involves. The lithography machine itself is a more than crores. So instead of, that's why it is not cost effective. And for the BioMEMS, I told you require the cost effective technology, and there is this soft technology is soft lithography is very much useful. What you need a very good master mold. What we call it is a master mold, just like a stamp. You have to make for my say. Everybody has a stamp. A stamp means the what I'll say the post office stamp and all. You have the master mold. You should have a master mold that you can fabricate commercially, or if you have your own fabrication process, then that you can make it in your own lab, in either using the silicon or glass or whatever, but it should be solid in nature, rigid in nature. And the pattern what you want to do finally in the master mold, you should have just a negative of that. Once you fabricate, then you can buy the PDMS. PDMS is a low cost material. Two part polymers, you can buy it. It's a low cost. Mix up, you will have a oven, you will have the other your spinner and all that you can manage easily. And then you pour the polymer on your master mold, do the spinning process, and do the polymerization at a high temperature, 100 degrees centigrade. All this, you have to optimize that. And once polymerization is over, then you can easily peel off. And that way you will get the device, replica of your design on the polymer. Yes. And if you want more, then it is available in the net. It is the soft lithography process. All the details are available.
Okay, sir. Thank you so much. Thank you.
Okay.
Thank you, sir, for a nice informative session. You connected MEMS with BioMEMS and fusion of technology at micro scale, and then also shown your research work for different biomedical applications. So thank you very much, sir, for being here. Thank you very much from all the participants, and particularly from the Sardar Patel College of Engineering and Atal sponsored course. Thank you, sir. Thank you very much.
Okay. Thank you all.
So participants stay here. We will be having session by Dr. Rudra Pratap from IIT Bangalore right now at 11:30. So attend that session. We will have, if we can take 5 minutes break, and we will start the session at 11:30 sharp. Professor Rudra Pratap Rao from IIT Bangalore will be taking this session. Thank you very much.
Sir, Bhole, sir, Kiran Bhole, sir, please share this PPT, sir. This Soumen, sir, PPT.